Hi everybody. Sorry I can't be there. We are going to do our notes virtual today. And we are going to talk about inclined planes. And you just need regular paper and you don't even need a calculator. We're going to be doing a lot of derivations. I'm just going to draw a ramp to represent an inclined plane. There you go. We will list it with theta. Put some object on the inclined plane. We're going to do 3 scenarios. The first one we're going to do is equilibrium. Equilibrium means that its acceleration is 0. It could be constant speed. It could be at rest. Okay, so rest or constant speed. All right, so we have to designate. So you can kind of think of it like everything was flat before and we're just tilting our little world here. Okay, we have to set directions. So generally we think things go down an inclined plane. So we're going to say down the inclined plane is positive, up the inclined plane is negative, perpendicular going like up into the air is positive, and going down. So it's kind of like X and Y. Excuse me. But instead of doing X and Y, we're going to call anything in this direction parallel, anything this direction perpendicular. All right, so let's start with a free body diagram. Okay, there's the block. We know gravity pulls down. We know friction is parallel to the surface and away from the motion. So we're going to have kind of and again, we try to make these somewhat parallel. We don't know the exact lengths. Oops, FG, or you could do FW. And of course, we have the surface pushing back. We put in gravity. All right. Sometimes if a problem says be specific where the arrows touch because of what they do, you would actually put the friction arrow right on the surface. Gravity would be at the center and the normal would touch the surface because that's where they come from. So let's label these. And this is your free body diagram. It's essentially going to be the same one for all 3 scenarios, but we'll sketch it. So the part that gets people is what's making it go down. So you have friction holding it up. The normal force is the surface pushing. There is a part of the object's weight that pushes down on the surface. Call this F perpendicular. And there's a part of the weight that's being pulled down. We call this F parallel. And then we notice there's a theta here. An observation would be that if I put these here, I put a little triangle. If I put a little triangle in there and I take it and I flip it over, I essentially get a similar triangle. I'm going to just sketch that over here. So here's our mini triangle. And this side becomes mg. This side becomes F parallel. This side is F perpendicular. You can just flip them again. F perpendicular ends up on the bottom. F parallel over here. MG is the longest side. And then theta would be in here. So if I use my sines and cosines, that means this is opposite. So the sine of theta times mg would be this side and the cosine would be here. So FG equals mg, or you can think of the side as equaling mg. F perpendicular is going to be mg cosine theta, and F parallel will be mg sine theta. So we're going to use that same configuration. I won't rederive it for all of them. All right, so instead of doing Fy and Fx, we're going to do F perpendicular. So we're going to do summation of F perpendicular. And we'll do that. Okay, so this is the forces pushing up or down on the surface. kind of like F normal. And then F parallel, because we're not doing a summation yet, sorry. Okay. Forces acting along the surface, which usually is gravity or friction. So when I say parallel to the surface, I want you to think, I use my pen as it, this F parallel, the component, that's parallel to the surface. Friction is parallel to the surface. F normal and F perpendicular are perpendicular to the surface. All right, so let's take a look at these. So summations, sorry, we'll lose the picture here. F perpendicular, oops. All right, so if I go to my picture, perpendicular, I have F normal, which is up, minus F perpendicular, which is mg cosine theta. And remember, everything equals ma. Well, you're gonna find in every one of these, unless the thing's flying off the ramp, perpendicular is always gonna be 0, and we end up getting F normal equals mg cosine theta. Plain and simple, don't overthink that. In F parallel, this is the one that's going to always help us solve for the acceleration. All right, so going down the ramp, positive direction would be mg sine theta, and going up the ramp, in negative land here, would be friction. So we have mg sine theta minus ff equals ma. All right, so in this case, because we're at rest or at constant speed, ma is 0. So both of these end up being 0. Typically the F perpendicular will almost always be 0. So what we're going to solve for, since there is no acceleration, is we solve for mu. Well, mu is friction force over the normal force. So let's see, we have m, let me back up a second. Because these are equal, it would be like this, mg sine theta, my bad. So we have mg sine theta over mg cosine theta. So you see a whole lot of things cancel. So it ends up being mu is equal to the tangent of theta. So there's a shortcut to figuring out mu if you know something's at constant speed or at rest. All right, next scenario. Let me move my paper. Maybe. All right, so let's call this example 2. That could be example 1. So the next one would be, let's call it acceleration with no friction. It's kind of an easy one, actually. So I'm going to draw the ramp. I'm going to put an object on it. We're going to have mg. We're going to have F normal. I'm not going to put friction in here. Okay, so F normal, Fg. The components, mg cosine theta, mg sine theta. Parts of the gravity that pull it down. Okay, so I'm not going to redraw the free body diagram. It will be exactly the same. Let's do the summation of the forces perpendicular. So we have F normal up minus mg cosine theta equals ma. Well, again, unless it's jumping off the ramp, ma is going to be 0. So that literally just gives us this. And in a lot of cases, it's not anything I even have to use. It's the parallel one. Okay, in parallel, we have no friction. So all I have is mg sine theta equals ma. And since it is accelerating down the ramp, I can't just make that 0, but I can do this. I can cancel out the m's, and you simply get acceleration is gravity times the sine of theta. That'll come in handy for those kind of problems. Okay, so the first one was at rest. All we were finding was mu. We know the acceleration is 0. If it's sliding down, it's as simple as just gravity times the sine of the angle. All right, last situation. Let's back down. This would be number 3. Accelerating with friction. All right, this one's a little more complicated. Again, the free body diagram will be no different. Here's my incline, my ramp, and my theta. Here's my object. So we know we have gravity, Fg, also mg on the side. We have F normal, and again, if I want to put it specifically, it would be at the surface, although we tend to put them at the centers. And then we have friction. So the incline plane free body diagram, unless you have no friction for some reason, is exactly the same. So I guess let's go back to the second one. I take that back. So this one, go back to number 2. Your free body diagram would just be the 2 arrows. So I take that back. They can't be exactly the same. All right, we're going to continue number 3. This one would be the same as the first one. All right, let's do the components. So I have F perpendicular, which is mg cosine theta. I have my mg sine theta, knowing my theta is here. All right, let's talk summations of F perpendicular. All right, so we have F normal minus mg cosine theta. You're starting to see a pattern, equals ma. And that's going to be 0 because it's not jumping off the incline. That just means the normal force equals mg cosine theta. So you see a pattern. Now, remember, friction force equals mu Fn. So friction is equal to mu mg cosine theta. Sorry, move that up a little bit. That's typically why we need to get those vertical forces. All right, let's go to F parallel. All right, so we have going down the ramp, mg sine theta. Going up the ramp, we have friction force, and it equals ma. It is not 0 because it is accelerating. At this point now, we're going to take this and substitute it in. That's part of why we do that. So we're going to get mg sine theta minus mu mg cosine theta equals ma. So you will see, we're going to take out all the m's. We're going to bring the g out in front, and we're left with sine theta minus mu cosine theta equals a. And that is going to be our formula. You're going to use parts of this to solve some practice problems. You may use all of it for some practice problems. All right, watch it again if you need to do it again. Thanks.